Hi everybody, I'm Emily Thompson, and my primary role this semester for our project was to manufacture all of our iterations for the prosthetic finger. Thanks. Our initial idea was to design and build an above-the-knee prosthesis. However, through additional research and some discussion amongst the group, we decided to be a little too big and expensive for our iterative design and manufacturing process. So along the same lines, we came up with the idea of doing a prosthetic finger, and we knew that the small size of the finger would allow for ease of that iterative design and manufacturing process I previously discussed. We also knew that this gave us the opportunity for design enhancements to both the finger and the wrist harness. So overall, the purpose of our project is to create a prosthetic finger design with a natural feel that is lightweight, flexible, strong, comfortable, and most of all affordable. And that brings me to the goals of our project. First, we wanted to consolidate the parts. What we found on Thingiverse had a few different STLs that would later be assembled, so we needed to consolidate those to meet our project requirements. We also wanted to reduce the post-processing time. The Thingiverse STLs required some sanding, filing, and drilling, so we wanted to tidy that up. We also wanted to create customizable attachments that provide additional functions. And we also wanted to introduce a new harness design that increased leverage and reduced pressure on the hand when going through the natural movements of the finger.
Hello, my name is Steve Stumbo. My part in this project was centered around the design process. So we pulled the original idea from Thingiverse and brought it down with its STL files. And as we were playing with these files, actually as I was playing with these files in a variety of different softwares that was suggested in the class, it came pretty evident very fast that we were dealing with STL files with a huge number of errors. I think one of the parts of this assembly had over 300 errors in it, and I was just struggling with trying to figure out these software packages to try to fix these errors. So we made the decision fairly early on that we would go ahead and redesign the whole finger, actually redraw it in Creo. And so as we did that, then we came up with our design improvements. It's hard to see from the picture here, but you'll notice that this middle section of the finger is made up of a couple parts. We integrated that all into one piece in this side over here, and we also did some better smoothing and blending in the design to make it look better. Probably the biggest key piece that we did that was different than the original design is in order to meet our articulating finger requirement of 2 joints, we took these 2 specific joints here, and in the original design they used metal pins that actually was assembled after the fact. And we said, no, we're going to create this main middle section, which is made up of 3 parts here, minus this socket and the finger, and we integrated that all together. So we got our 2 articulating joints out of that that were printed at once, and then we were able to sculpt and combine this middle section part into one single part as well. So at the end of the day, we reduced the number of parts. It did take significant time to redraw this. I think it was mentioned in class that it's really difficult to take somebody's design that's an STL and back out all the dependencies of how that was made and so on, and that was very true. I basically started from scratch here. The one thing I will say is we did integrate 3 threaded joints in this design, and I'll try to get up here in the camera. You can see in there that those screws show, and then the one in the base is in here as well.
All the finger components were printed in the Projet 7000 by 3D Systems, so that encompasses the fingertip, the articulation component, and also the finger socket. This is done with an SLA process and was printed in a plastic material that is clear in color. We thought it would be kind of neat to see the inner workings of how the finger, kind of flexes and extends by all of the wires and cords running through and across the knuckles. This Projet 7000 is especially good for use in prototyping. It prints with a fine featured detail with accuracy of up to plus or minus 50 microns. We built our finger in 100 micron layer thickness, so that accuracy is about half layer thickness. Our build duration ended up being about 4 hours and 15 minutes, and this was for our final finger plus a duplicate just in case anything may have happened in transit or in assembly.
My name is Lance Yellowhorse, and I was in charge of the palm harness design for our prosthetic finger. Today we're going to talk about the CAD revisions, .stl mesh repairs, the slicing, printing, post-processing, and assembly of our palm harness design. The palm harness was an original .stl file created by Swoozle on Thingiverse. Our goal was to modify the palm harness for comfort, adjustability, strength, as well as support for the articulation of our prosthetic finger. The .stl was originally a mesh file that was converted into a solid body. 70 errors were repaired using ANSYS's space claim. This video shows errors including split, duplicate, and inexact edges, as well as missing faces. Once the .stl file was free of errors, modifications were made to elongate the straps for strength and adjustability of the buckles. The file was then uploaded into Cura's slicing and printing software, where a brim was applied to assist the bonding potential between the bed and the nozzle, and each layer is examined for quality. Now that the palm harness fits within the build volume, the print is initiated on the Idea to Product Labs R2D2 Flexi extruder, and we can see the NinjaTech SemiFlex TPU flexible filament being fed into the RAM extrusion head. This controls the feed rate, material, state, and precise movements relative to the bed. The goal was accurately to maintain the size and shapes of the rods, maintain convection and conduction, as well as monitor the position and control of the printer. We chose this printer due to the reduced cost, 20% infill providing structural rigidity, and flexible material capabilities, soft feel, and ability to withstand high tensile strengths. The palm harness is designed for the right hand and can be modeled for the left hand as well. The video shows a square opening where the anchor block will be applied. I will talk about this part shortly. These images show the final part quality of the palm harness, and the same process was repeated for the wrist straps as well as the palm straps. The anchor block was created using the Idea to Product Labs Stratasys Inkjet Object 30 Pro using RGD 450 and simulated propylene, giving us a tough, small, precise anchor block that will anchor our tendons. For assembly, a design change was utilized using Loctite superglue to bond the straps together in place of soldering, which will create a weaker joint. The straps were designed to have rods facing rods to increase surface area, adhesiveness, and visual presentation. The straps were fit into position and clamped during the curing settings. This same technique was repeated for the buckles. This is how our palm harness was designed.
Hi, my name is Justin Felix, and my portion of the additive manufacturing project this semester involved creating the final visual presentation for our project. I'm actually located on the west coast, about 1,200 miles away from the rest of the team, so unfortunately it made it impossible for me to participate in the physical build. So instead I'm going to discuss a few lessons learned from the team as well as how team dynamics played into this project. One of the biggest lessons learned or really reinforced is that even in additive manufacturing, the process of getting from idea to final product is very much an iterative process. As we previously discussed, we made multiple adjustments to the middle portion of the design to create a better blended and functional product whilst reducing the number of parts printed. One thing we discussed multiple times in class was systematically engineering a part to reduce the number of times that a product would need to be printed before finally getting a part that fit the fit, form, and function desired. Thankfully, we were able to accomplish this in just 2 prints, even with a team that's relatively new to additive manufacturing. I think we also learned a good deal about how to plan for the strengths and weaknesses of each type of printer and designating parts to be printed or manufactured on printers appropriate for the needs of that design. For example, the fingers required a higher degree of accuracy to ensure that the parts were able to actuate with a tight tolerance, but were not completely adhered together. We actually ran into this issue in our first print, as the spacing was too small and the rods glued together, making the fingers unable to be used. So for this reason, we printed the finger portion on the ProJet 7000, whereas the harness that required a little bit less precision could be printed on the R2D2 without 100% infill. Finally, the team had an additional hurdle to clear, being that all students were online, so any products that we wanted to collaborate on, we had to upload or email to each other, and response times from the team varied vastly depending on what other work each team member had to do outside of the project. I think this created an interesting dynamic in that we got to experience what a company may have to overcome if not all portions of a product are sourced, designed, and manufactured in one location. So our team had to overcome distance, time zone differences, and the fact that team members are employed outside of this project as well. Thanks for watching, and I hope you enjoyed our project.